Hi viewers, welcome to all. Here we are discussing about a project ReAdapt, a reconfigurable datapath for runtime energy quality scalable adaptive filter. ReAdapt is a reconfigurable datapath architecture proposed in this study for scaling the energy quality trade-off of adaptive filtering at runtime. By reorganizing the processing flow in the datapath and limiting the switching activity of unneeded modules using data gating, the ReAdapt may dynamically pick 4 adaptive filtering methods for grading complexity level during runtime. Okay, the ReAdapt approach scales the energy quality trade-off by selecting one of the 4 degrees of filtering algorithm complexity. Okay, so here we have used 4 filtering algorithms. So one is a LMS, least mean square, and another one is a PU-NLMS, partial updated normalized LMS, okay, and SM-NLMS, okay, set membership normalized LMS, okay, and normalized LMS. Okay, so this 4 method we have used here. The ReAdapt designs reuses common model of each adaptive filter, resulting in a VLSI hardware implementation that is a compact. Okay, so in this case study, the ReAdapt architecture's operations is evaluated using 5G input sequence of noise and desired signal. In order to avoid complexity, this work was designed using accurate restoring dividers and coupled with the update control block of LMS adaptive filter. The synthesis result of this 4 distinct level of filter algorithms comparisons with the 2 different multiplier architectures will be demonstrated in Vertex 5 FPGA, and outcomes of area, latency and power will be studied. Okay, so here the improvement of the project we have developed with to design 4 different adaptive filtering algorithms using 2 different multipliers and prove the performance of area, delay and power. Okay, for existing architecture development we have used as a traditional binary multiplier design, and for proposed architecture development we have used a reversible valence tree multiplier using a TOEFL, Feynman and Priest gate architecture. Okay, and additionally exact restoring dividers was integrated in the update control block of LMS adaptive filter for more high performance level. Okay, so now we can verify the base paper. So this base paper, so we have already discussed, they are developed as a 4 different adaptive filters. Okay, so one is a LMS filter, okay, second one is a NLMS filter, and third one is a PU-NLMS filter, and fourth one is a SM-NLMS filter. Okay, so here this filter architectures they are given in figure 1 and figure 2. Okay, so the figure 1 is a core architecture of this paper. So how they are processed this generalizations of W coefficients ReAdapt architecture. Okay, so here the figure 2 they are given in detailed architectures. Okay, the detailed architectures of the full designs given in figure A. Okay, the figure 2A. Okay, so here we have zoom it and we can verify the architectures. Okay, so here xk is the input signal. Okay, that input signal here they are given as a ECG signal, but we are given as a 5G input sequence. Okay, at 1 GHz input frequency it will be taken from the RF antenna. Okay, and this decay is a desired signal. Okay, so this input signal and desired signals will be entered here. Okay, so initially it will be started with the core architectures. Okay, so once the core architectures configured, okay, with the selector is the input sequence that is selecting the filters. Okay, that means here you can verify the table 1. Okay, so here 00 means LMS and 01 means NLMS and 10 means PU-NLMS and 11 means SM-NLMS. Okay, so here they are given the process. Okay, so initially the core architecture start with yk equal to wk into xk. Okay, so it's same as a normal filter. Okay, that means coefficient into input. Okay, and ek, so ek is the error. Okay, so ek equal to desired signal minus and yk signal. Okay, the coefficient mixed with signal, right, that signal. Okay, so as per this we have generated a error, and this second and third level of core will be updated with the feedback output. Okay, so here the main focused is a feedback one. Okay, as per the multiplexer switching of selector mode, we will switch the LMS, NLMS and PU-NLMS and SM-NLMS mode. Also we have switched with the feedback inputs. Okay, so here you can verify it, the architecture. Okay, so this is a full design architecture. Okay, so here the selector will switch the multiplexers. Okay, so here you can check the input of the multiplexers 0, W1 and R1 and W0, R0. Okay, so it comes with the feedback, and they are used as a two multipliers in the core architectures. So this two multipliers we have remodified with the binary multipliers and velocity multiplier. That velocity multiplier architecture is also developed with the reversible architecture. Okay, so that reversible architecture functionality designed with this type of architecture. This is a partial product generations of velocity multiplier. Okay, so it will be generated with the TOEFL gate and praise gate based architecture. Okay, and the update control block, they are used one divider. Okay, this divider functionality we have used with the exact divider. Okay, this is a restoring divider architectures. Okay, the architecture given in figure 2 and also figure 1. Okay, so as per this diagram we have developed the two different architectures. Okay, so dividers and this multipliers. Okay, and normal binary multiplier. Okay, so once we start the design, okay, we will integrate the multiplications, addition part we are used with the ripple carry adder. Okay, and this designs will be developed in a Verla HDL. Okay, after this full design of LMS filter, okay, so figure B started with the LMS mode. Okay, so it will be considered with only the decay signal. Okay, other signal will be optimized. Okay, so RS, okay, and SM-NLMS comparisons. Okay, this will be optimized. Okay, so it will be considered as a decay. Okay, with the support of selector, it will be present with the feedback output. Okay, and after that the section C will focused for NLMS. Okay, NLMS also PU-NLMS mode. Okay, so this NLMS is a normalized LMS. Okay, so and the PU-NLMS mode. Okay, so consider with the RS input and decay signal and XK signal. Okay, so as per that it will be generate the output. Okay, and SM-NLMS, okay, that is a mainly the proposed architecture of this paper. It will be focused with to reduce the negative iterations. That's why it will be taken the 2's complement. Okay, after that it will be processed this output. Okay, so this SM-NLMS comparisons, okay, will be focused with the additions and comparisons. Okay, after that it will be generate the NLMS output. Okay, so that output will be given to the update controller block and it will be come with the feedback output. Okay, so first of all we will see the simulation part. Okay, and the Verla HDL coding. Okay, now okay, so this is the top model architecture of this Verla HDL coding using with the binary multiplier. Okay, so here we have configured the selector. Okay, so this selector we have possible to switch. Okay, here 00 means LMS, 01 means NLMS, and 10 means PU-NLMS, and 11 means SM-NLMS. Okay, so here we are configured the core logic, complement, okay, and SM-NLMS, error, update control, all the blocks. Okay, we have all the supporting codings. Okay, and this is a second level coding of the reversible velocity multiplier 8x8 architectures. Okay, so this architecture partial product generation started with, okay, Fiamin gate and TOEFL gate. Okay, so as per this level of architecture. Okay, and the multiplication output of simulations, it will be given here. Okay, so A, B, product and multi-check. Okay, you can move cursor and you can check anywhere, and you can check the multiplication check value exact versus the output of the multiplier. Okay, so you can check anywhere. Okay, it will be accurate values only. After that we have synthesis this multiplier code. It will be given the parameter output as a number of slice registers, number of LUTs, occupied slices, IO base. Okay, and this is the RTL schematic. Okay, so here you can focus the multiplayer internal architecture, Feynman reversible gate. Okay, and Priest gate. Okay, and the partial product generated with TOEFL gate, Feynman gate. Okay, so this logic gate is a purely reversible one. Okay, Feynman gate means, okay, so this is the internal architecture. Okay, so after this multiplication part, we can show the simulation results of the LMS adaptive filter. Okay, so here you can check, this is a SM-NLMS. Okay, so this is a error signal. Okay, so error output. Okay, and this is the input signal, and this is a desired signal. Okay, here you can check it, we are given a clock frequency at 1 GHz frequency, and we can change the mode and we can test it here. And before that, and this is a simulation output for the multiplier, reversible velocity multiplier used with the LMS adaptive filter. Okay, so here we can change the mode. Okay, and we can check it. Okay, now we are already shown at 1 1. Okay, now I'll given a 1 0. Okay, after that we will run it. Okay, so this is a 1 0 output. Okay, and if you need 0 1, that is a NLMS mode. Okay, so it's mainly focused for RS versus desired signal. Okay, so it's the same like as a desired signal output. Okay, and 0 0, it's purely LMS. Okay, so we are given decay signal only. Okay, so this is a 0 0 output. Okay, so here you can check the architecture. Okay, so the desired signal will be subtracted with the RY, but the feedback of this signal is the same desired signal. So initially the RY start with a 0. Okay, so here it will be shifted. After that we are taken the output. Okay, so here the high priority given the value for desired signal only, that's why it will become with the same desired signal output. Okay, so here you can check the inputs and outputs of the filters. Okay, and this comparisons we have done with the Xilinx Vertex 5 FPGA. Here you can check the adaptive filter. Okay, so here it will be take slice registers, LUTs, and occupied slices and IO base. Okay, and synthesis report we can check with 24.183 nanosecond. Okay, and RTL schematic okay, you can check the core logic, update control, and error signal. Okay, so as per the input mode, okay, so other components will be optimized. Okay, but here the input mode is 1 1. Okay, so here you can check the RTL schematic. Okay, so here once we are given the input signal, okay, so it will be taken in core logic. Okay, so this core logic will have a two multipliers, reversible, okay, reversible velocity multiplier 8 cross 8. Okay, so this reversible multiplier will have a Feynman reversible gate, Priest gate, partial product. Okay, so already we shown. Okay, after this multiplication part, it will become with the multiplexers and ripple carry adders. Okay, and this output given to RS or Y output. Okay, so given to the error. Okay, and yes, SM-NLMS comparisons. Okay, it's having a comparator. Okay, and the error signal having a subtractor. Okay, so after this it will become with the update control module. So this update control module designed with the exact 8/4 divider. Okay, so here exact 8/4 divider designed with the exact divider cell. Okay, so exact divider cell. Okay, so this cell architectures will have full adders and the register. Okay, so it will be present with this one. Okay, so full adders versus multiplexers. Okay, and after that we are taken as a final output. Okay, so this comparisons we are updated in the comparisons document. This is a binary multiplier based comparisons. Okay, and this is a comparisons analysis chart for 4 different modes. Okay, and this is a comparisons for reversible velocity multiplier, the TG and FG partial product generations. Okay, with the 4 different mode of comparisons, and this is a comparisons analysis chart. Okay, and finally we are written abstract document. Okay, so here you can analyze the base paper abstract, improvement of the project, proposed title, proposed abstract, existing system, disadvantages, and proposed systems with the related notes. Finally, literature survey and references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.